get started again. We have the geoscience keynote of 1 hour until 12:30 when we'll go to lunch. This is Tobias Keller. He's at Oxford right now and soon to move to Stanford. So thanks, Tobias.
Thanks to the organizers for inviting me. I'm going to speak about computational models of melt transport from the source to the surface, and I quickly want to acknowledge people I've worked with on these things. Rich is one of them. I'm working with him at the moment and have been doing so for the last 3 years. Boris was my PhD advisor. He's going to speak later today. Dave May has spoken earlier in these workshops, and Mark is our petrology visit, helping us out with some of the models you're going to see during this talk. So what this is all about is, you're well aware of what this workshop is about. Silicate melt transported through a deforming host rock, and magmatism in the Earth, just to kind of open the focus a little, is a really important system in the sense that it is a key ingredient in the evolution of our planet. It has a key role in the thermal and chemical evolution. It couples the subsurface to the surface environment by volcanism. It has great implications for humanity because of hazards associated with volcanism, but also because of resources that have been emplaced by magmatic processes. And so there's a lot of expressions of magmatism in the Earth, and we have a lot of interest to understand them. What we have in terms of observational constraints is quite a wealth, as we have also seen in other talks during this workshop and other workshops. There's field geology, petrology, geochemistry, geophysics, geochronology. But one of the issues with practically all methods of observing magmatic processes is that they give us snapshots of the system, and particularly in the geological record, they give us snapshots of the dead magmatic system, not the live one. With geophysical methods, we can see some of the magmatic systems in action, but we're struggling with resolution, and also the rates of many processes are slower than a human lifetime, or the lifetime of a PhD, which is even shorter and more relevant for science. And so really we're talking about snapshots, but what the challenge is, and what I'm going to try to talk about, is how do we gain an integrated understanding of magmatic system in space and time, and in particular from the source where magma is built all the way to the surface. And I'm going to start this out with a bit of a motivation. This is a proof of concept simulation that has never been published because there's a lot of issues in there that would have to be resolved, but it shows the direction for which we're aiming. What you're going to see is melt fraction, the shear viscosity, some proxy of composition where blue is more mantle-like and red is more crust-like, and temperature. And I've imposed the melt source down here. I've imposed an extensional strain rate on the relatively tough lithosphere, and then we can see what happens when we run this simulation. What can see happening is some form of channelized melt intruding into the base of the lithosphere, where it thermally erodes, deposits more crustal-like compositions by crystallization, and at some point one of these fingers actually results in a fracture as it reaches the flow-to-fracture transition, and so melt can actually protrude into the brittle part of the lithosphere. So this is really what we mean by from source to surface. How does melt get from where it melts down in the upper asthenosphere all the way ultimately up into the surface? And the reason why you can only see the run up to here is because afterwards it failed. And I'm going to mention later on why these things are challenging to run. I'm going to structure this hour into 3 big blocks. The first one is just going back to the physical model, because this is what the workshop really is about, is to discuss how we build the physical model and how we can work with it. And then I'm going to show you 2 particular applications or 2 particular problem sets on the way of melt from the source up into the surface, one of which has to do with reactions, how melt is produced and how the melt production actually couples to the transport processes. And then the second big block is going to be about the flow-to-fracture transition, because we all know that hot rock creeps whereas cold rock fractures, and melt encounters both types of rocks from its source up into the surface. And so this is going to be an interesting one as well. And so we're going to start out with the physical model. I'm going to take just a slightly different approach in introducing the equations that you've now seen probably tens of times, because what we're going to be interested in is not just the specific case of two-phase flow, but what we really want to look at is conservation of mass for a number of phases, which are physical material states like liquid, solid. You could also add vapor phases, although that's not something we're dealing with. but I understand maybe Chloe is going to talk about that later on. And a number of chemical constituents or components. And so essentially what we need to do when we formulate the physical model is start with conservation of mass, where we have an equation for each of the phases and an equation for each of the components in each phase. And here the notation is that those J indices number the phases and the I indices number the components. And essentially phase mass conservation is quite simple, where the changes of phase mass over time are made up by the divergence of mass flux of that phase and the reaction rate which transport mass between the phases, and all of the phase reaction rates need to sum up to 0 so that we're not overall producing or destroying mass. And it's very similar for components, where the change of component mass in time is made up of the divergence of the mass flux of that component and the reaction rate of that component, so that's the mass of a specific chemical constituent that is transported in melting or crystallization reactions. And there can also be a diffusive or dispersive flux included into these equations for composition. And as you can see, all of the component-wise mass transfer rates for one phase are going to sum up to the net phase reaction rate. I'm going to come back later on to explain a bit more about these reaction rates. It's just the general system for now. And then if we're interested in not only what mass is doing, but also how the system dynamically moves, then we're interested in conservation of momentum. And this again is just a general way of writing the Stokes equation, really, where J again is the phase, so we write one conservation of momentum equation for each of the phases we wanted to deal with. There's a divergence of shear stress involved, there's some pressure gradients involved, some buoyancy forces, and then crucially a phase interaction term. And if this phase interaction term is written according to Darcy's law, then these equations for two phases can recover the Mackenzie's equation that we've seen most often during these workshops. And again, all of these phases, in the absence of surface tension, I should mention, sum up to 0 so that there's no net force between all of the phases. The last conservation equation that we are adding to this system is the conservation of energy, particularly when we're interested in reactions. There's energy involved in melting rock or crystallizing rock, and so here's the energy equation written in one form. There's many forms you could write this. This is written in terms of sensible heat, so that changes in sensible heat are made up out of thermal diffusion, adiabatic work by compression or decompression, viscous dissipation, and latent heat of reactions. And you can see here again the I indices come up because there's reactions and latent heat and can be specific for any chemical components included in the model. So with all of these general equations, what we did with them is we took them and reformulated and simplified them slightly for two phases and generally for n components. So we didn't want to from the beginning limit how many chemical components we can deal with, but we already knew that we're only going to deal with solid silicate rock and a liquid melt. And so the equations in the simplified form, maybe you can see some of the familiar patterns. So there's a conservation of bulk, momentum and mass, which is the same as what Sander in the previous talk called the two-field formulation, or they're actually very similar to or identical to the Mackenzie equations from 85. And you can see that there's a shear stress term in there and a compaction stress or compaction pressure term. And both of these will depend crucially on the shear and bulk viscosity, shear and compaction viscosity, and I'm going to come back later to how we can describe these viscosities to include quite a lot of rheological effects. There's a permeability and the liquid viscosity. I'm not going to say much about these because they've been covered elsewhere, and actually liquid viscosity is a bit of a complicated issue because it depends a lot on composition. I don't want to discuss that right here. And then we have a system of equations, a second one, which all of them are time-dependent equations, and they give us the thermochemical evolution that can be coupled by the velocities to this to the dynamic system, the fluid dynamic system on top. And you can see that there's the conservation equation for energy, for phase mass, and here we only have to deal with one phase because the second phase is just one minus the first one. And then these two equations are actually repeated for each of the components, so they contain the index I. So essentially for n components, there's 2 times n equations that are formulated. One is for the conservation of components in the solid and one for the composition of the liquid. And here, to close this system of equation, we need to find some prescription for these reaction rates. And this is where I'm going to start the more application-oriented part of this talk, which is reactive melt transport. How do we actually describe these reactions? And to motivate this a little bit with an earth science problem, I'm going to look at the role of volatiles in melt transport beneath mid-ocean ridges. And in particular, the interest about what dynamics of reactive melt transport, what effect they have on mid-ocean ridge system. And obviously, I'm implying already that the volatiles will have something to do with reactive melt transport. I'm going to come back and explain that in more detail. And in particular, we're interested in what the effect of water and CO2 are on the magma dynamics beneath the mid-ocean ridge. To just quickly introduce and motivate this is, from experiments, we know that both water and carbon dioxide depress the solidus of peridotite melting beneath mid-ocean ridges by quite a dramatic amount, so from about 70 kilometers all the way down to a couple of hundred kilometers potentially. And that if we're thinking about a world where the melt production is controlled by upwelling velocity, lowering the onset of melting means that we're widening the triangular region in which most melt is produced. And so the question really is, what happens to these deep, volatile enriched melts that are produced over a much wider area of mantle, and then just a little triangle up here, which is the traditional volatile free melting regime that we're all familiar with. And just to kind of show you again the canonical view of how melt focusing works. This is also what Andy's been talking about yesterday. So essentially, melt is generally traveling upwards due to its buoyancy, but then there's some processes up here. One of them is ridge suction. The other one is flow along an inclined plane, because there is some sort of a flow barrier which can be introduced by crystallization and or rheology. And the question really is, how do we extend this to a much larger melting system? What happens to these low melts down there? And then the second piece of information that we're interested in is that there's geological evidence for channelized melt transport that has been interpreted for a while in terms of dissolution channels, where a melt that is undersaturated in phases like OPX or orthopyroxene flows through mantle rock, dissolves the orthopyroxene, leaves behind dunite or olivine-rich rock that can be identified in the field, and that has led to the idea that there might be a coalescing framework of channels beneath a ridge axis that channelize melt quite efficiently into the ridge axis, and some simplified models in upwelling column geometry have recovered systematics that look pretty much like the idea of that model. And so the question really is, what do volatiles add to this picture? Do they give any additional information about channelized melt transport? So now we come to the question of how to actually prescribe a reactive melt model. And for anyone who is marginally familiar with multi-component silicate thermodynamics knows that this is a kind of worms that is very difficult to deal with. So our approach to this is a very simplified one, but we believe that it can be useful for some context. So I'm going to try to make that case. So we're calling it the reactive disequilibrium-driven multi-component method, or short run DMC. And there's a little MATLAB code that essentially captures this method, and you can download that for free on Bitbucket. It's an open source little code that will help you to kind of play with this system and see if it could be useful in one of the contexts you're dealing with. The basic idea of this model is that in order to find equilibration reactions, we need to first define what we mean by equilibrium. By equilibrium, we mean that there is some combination of pressure, temperature, and bulk composition for which we want to know the equilibrium compositions of the solid, the rock, the liquid, the melt, and what the equilibrium proportions of the melt with respect to the rock are. And in this parameterization, what we do is we define partitioning coefficients for each of the components we want to deal with. So this again can be generally n components. And these are parameterized in pressure temperature space according to thermodynamic relations derived from ideal solution thermodynamics. And there's, I think I showed the reference before, there's a paper by John Rutsch, Dave Berkovici and Mark Spiegelman, who actually, I think, does a marvelous job in introducing how these thermodynamics work. And I would really recommend you read that paper for some more information. So we have a definition of thermodynamic equilibrium that is quite cheap to compute and easy to use in a kind of a large-scale geodynamic code. then the next piece of ingredient is that there is a system evolution. As soon as we switch on the dynamic evolution of these systems, there's a time evolution of pressure, temperature, and bulk composition due to flow, due to thermal effects, and so on, which means that even if we start the simulation at equilibrium, as soon as we take one time step, the result of that time step is going to be in disequilibrium. And in order to drive the system continuously back to its equilibrium, we apply reaction rates. And now, if we know equilibrium, we know the current state of the system, there's various ways how one could actually prescribe these, and we do a very simple linear kinetic approximation or linear kinetic parameterization for these reaction rates, which capture some of the ideas that there might be a specific composition of melt that is being produced in melt reactions, and that could, for example, be the fractional melt composition. But then there might also be, in the second rate here, there might be mass neutral exchange reactions where a solid and a liquid, as they're in contact with each other, can equilibrate without net melt production just by sending chemical species back and forth. And so essentially we parameterize this simply as differences between equilibrium states and disequilibrium or dynamic states in the simulation. And we define this C gamma as our petrological model of what we believe the composition of net phase change should be. So if we're melting, what should be the incremental composition of any increment of melt produced, or the same for crystallization. And so this is a model that is very useful in the sense that it's very flexible, and it's easy to introduce into two-phase models. But what is less easy to do is how do we actually calibrate this system to reproduce what we think we understand of certain petrological systems. And for us, the petrological system we're interested here in is mantle melting with water and CO2, and I've just given you a selection of some of the outputs from both theory and experiments of how we imagine the melt systematics for water and carbon in the mantle to be. And one of the things you can see, for example, here, this is a pressure temperature diagram. You can see that the peridotite solidus is up here, and the carbonated solidus is quite a bit depressed. And the similar thing you can see here, where the diagram is rotated, where the dry solidus is this black line here, and then adding water does all sorts of complicated things to the solidus, which have to do with all sorts of different mineral phases that come in. So really what we want to do is simplify this picture and try to extract what we consider to be the essence, because you probably have heard this quote that all models are wrong, but some models are useful, and we approach petrology from that angle, where we say whatever we do that is simplified from the real petrology is going to be wrong, but we're trying to find what are the useful, simplest ingredients to reproduce some of this petrological system. And for us, what it is that we want to capture significant solidus depression. We want to capture that volatiles have an incompatible partitioning, so that means that they very much like to live in the melt rather than the solid. And they produce, as a result, deep, low-degree, volatile enriched melts that are produced below the onset depth of volatile-free melting. And the final calibration that we've come up with for the study I'm going to show next is essentially this, where you can see a pressure temperature diagram with the volatile-free solidus resulting from our parameterization, the hydrated solidus and the carbonated solidus, and the hydrated and carbonated are each with 100 ppm water or CO2 added to the system. And the actual components in our n-component space that we're using to discretize this is a 3-component space, both for the hydrated and the carbonated one, where we essentially where we say that the volatile-free mantle melting is captured by 2 components: one refractory, which is the leftover of basic basaltic melting, which is dunite and olivine-rich rock, and the product of basaltic melting, which in our case is mid-ocean-rich basalt. And then we add the volatiles to the system, not as pure volatiles, because they would have quite extreme behavior, but rather as a basalt-like silicate component with enriched volatile content. So in this case, this would be a carbonated morph with 20% CO2. That's, for example, motivated by the fact that the deep, low-degree carbonate-enriched melts would have of the order of 20% CO2 predicted by experiments. So this is essentially like the most extreme carbon-enriched melt that we want to produce in our models. A quick word about implementation, how we then go on to actually solve this numerically. The code that I'm going to show results from later on is a second-order finite difference staggered grid discretization. This is a very standard form of discretization, which is essentially the same procedure as Taras was talking about yesterday. We are solving it with a Newton-Kirchhoff method that is facilitated by Petzy functions, and we're solving the two blocks of equations separately, the velocity-pressure problem and the thermochemical problem, in the same blocks as I showed you in the slide with equations earlier on. We're using a second-order upwind advection scheme for the advection part of the time evolution equations, and we couple this to this n-component general run-DMC method, and all of it is, of course, parallel for free thanks to Petzy, and I cannot stress enough how convenient it is to work with Petzy. So anyone who is not yet convinced that that's a great tool, maybe come and talk to me. I can make a good case for it. So this is the code that we built, and the first thing we tried is take this to a relatively simple geometry, which is a 2D upwelling column model, where we simply created a mantle with 25% of the fertile basaltic melting component and 100 ppm equivalent of water and or CO2. And I'm going to show you the results. So this is a part of the model domain from 20 down to 100 kilometers of a carbonated melting upwelling column model. So I think, if I remember correctly, that was 4 or 5 centimeters upwelling rate as a boundary condition, and then all of the model evolution is just spontaneous behavior. What you can see here plotted is the bulk flux of CO2 through the system. And you can see that CO2 flux is concentrated into these subvertical channels. And if you look at the rest of the result, these channels are also enriched in melt, and they have a particular reactive behavior inside of them. And so what we did is we took this line across this most active channel here in the middle, and we've reduced some profiles across these steps by the horizontal average, so that we can just look at the deviation from horizontal average to get an idea of the systematics of what happens in these channels. You can see that plotted up here in terms of the composition of the liquid. So this is the fraction of components in the melt, and it's again the deviation from horizontal mean. And what you can see inside this channel, and also all of the other channels that are next to it, is that the carbonated basaltic component is preferentially enriched, whereas the volatile free basaltic component is preferentially depleted. And if you look at the same profile of horizontal deviation from horizontal mean in terms of the reaction rates for the same components, you can see that the dissolution rate of the volatile free basaltic component is enhanced, whereas the dissolution rate of the carbonated one is depressed. And you can see that this is scaled up to make it visible. Actually, it would be like near zero. And so what this is essentially a dissolution channel facilitated by an increased volatile concentration. As I've just talked about before, volatiles have a corrosive effect on basaltic melting. They lower the solidus and therefore increase the productivity. So if there is some places with an increased flux of volatile enriched melts from depths crossing into the stability region of volatile free basaltic melt, what is the result of it is an enhanced reaction rate dissolving the major component silicates out of the rock. And I should remind you that this is with only 100 ppm of CO2. So this is not like an arc melting context where there's a large influx of volatiles into the system, but this is just what we think is a realistic amount of volatiles for a depleted Morb source. And so if even for a depleted Morb source we have enough volatiles to induce this volatile flux-induced reactive channelization, we can actually say that this is potentially relevant for almost any context in which mantle melts at depth. Now, obviously, it's going to be interesting to put this into a mid-ocean ridge geometry and see what the consequences are. So you can see here the melt fraction, the magnitude of Darcy flux, so this is the relative speed of melt with respect to the host rock, and water concentration and carbon dioxide concentration on the right. And so this was run with 4 components, with a hydrated and a carbonated basaltic components. And what you can see is the plate is spreading to the right. The left-hand side is the symmetry axis, and this is a box of 2 by 300 kilometers. What you can see is that most of the melt is produced above about 70 kilometers, because this is how we calibrated the system. That's the onset of volatile-free melting. The melts that are produced below the volatile free melting depths are very low in fraction. and they are not very mobile. So they're separating from their residue at the order of maybe a centimeter per year. But as soon as we cross into the volatile free melting region, these channels that we've seen in the previous slide pick up again, but now they start to coalesce and be collected into the rich axis. So there is a focusing of a coalescing channel network. However, I should point out that all of these channels only exist at depths. So this is not exactly the same reaction as people have suggested to lead to dunite bodies. Our system is actually calibrated in a way that we do not find that melts that are being produced maybe at 50 kilometer depths continue to channelize because of silicate dissolution, because our model is simply too simplistic to include that reaction as well. But still, there is a way that channeling can have a much deeper onset than it would be suggested for OPX dissolution reactions. And just to kind of bring home the point that this is really the volatiles acting, you can see 4 models where one of them has no volatiles at all, another one has 50 ppm, another one 100 ppm, that's the reference model you just saw before, and one with 200 ppm, and you can convince yourself that the channelizing effect, that flow heterogeneity introduced by reaction transport feedback, is increased with an increasing amount of volatiles in the system. What I wanted to point out as well is that there's these orange lines you can see in each of these simulations, which are actually a calculation of what is the furthest distance away from the rich axis from where melt is still focused into the rich axis rather than ending up along the flanks, the young oceanic LAB. And so you can see that the increase in volatiles doesn't actually change this focusing distance at all. If at all, it is reduced a little bit by the increased heterogeneity of flow patterns with strong channelization. And so that means that all of those melts that are being produced quite far off axis, they don't actually end up in the rich axis, but instead they will travel upwards, as you can see in these red streamlines, and get stuck somewhere along the forming oceanic lithosphere-stenosphere boundary, where they will crystallize. Or maybe if we would include fracture processes, some of these would interact with fracture zones and create off-axis seamounts. But the point is that there's quite a sizable amount of volatiles that do not end up being released into the surface system, but instead refertilize and metasomatize the oceanic lithosphere. And that obviously is an important constraint for our understanding of deep volatile cycling and what volatiles are extracted and what volatiles might actually be recycled straight back into the mantle because they're stuck at the base of the oceanic lithosphere. Just to kind of sum all of this up for the mid-ocean ridge, so we've seen that there's a dry or volatile free melting region and an extended wet melting region below it. The melt streamlines have a behavior where, depending on the compaction length, so that depending on how far away from the ridge axis the pressure suction of the ridge can be formed, they either travel straight up where they would hit some sort of a flow barrier and be driven over to the ridge axis. And I should point out at this point that these models do not include all of the complicated rheologies and grain size models that Andy was talking about. So in our case, there's none of this additional effect of channelizing melt and focusing it more to the ridge axis. So there can actually be melt that travels all the way to the crystallization boundary and then is extracted upwards, and otherwise it can also be diverted by this ridge suction effect. But then there's a certain lateral distance away from the ridge axis which limits the focusing of melt into the ridge axis, and anything else happens to just get stuck along the flanks of the ridge and crystallizes there. I think now interesting for anyone in the room that has to do with implementing better numerical schemes, or maybe if there's mathematicians around who are interested in thinking about these problems from a technical point of view, there's some very strong challenges associated with these models. One of them is, and actually I think that's one of the most critical ones to get this right, is accurate mass conservation. So now we are interested in each of our chemical species being accurately conserved in terms of their mass. Now, the problem with the volatile enriched species in particular is that they have a very low concentration in the beginning of the run, and they have a very strong partitioning behavior because they have a low partitioning coefficient. So the ratio of concentrations between the melt and the solid and the amount, the relative amount of them being involved in reactions is quite extreme. And that actually means that if we have a compaction length which is not large enough for our numerical grid to resolve it, we get spurious results for the mass conservation of our volatiles. And this is, gives you an idea down here. So this is volatile degassing flux calculated at the rich axis for a number of different models. So this is just capturing the steady state of the flux arriving at the rich axis, and this dotted line gives you an idea of the expectation of what systematics they should fall on. And you can see that these points up here are massively above expectation, and actually this point here is of a value of 6. And unfortunately I've deleted the numbers on here, but 6 would be somewhere up here. So this not only is it not fulfilling our expectations, but I can actually show that is a mass error that is larger than the actual signal. And this is the carbonated result. So the more incompatible one of our components is, the more pronounced the effects are for under-resolving some of the flow structures in our model. And it's very important for us to find a way to describe the mass conservation equations that actually take care of not violating mass conservation, particularly for volatiles, because they have a strong effect on thermodynamics. And one of the things that I think is at the root of this problem is that the reaction term in these equations very sensitively couples with the advection scheme used. And so you might recall that I said that I'm using an upwinding scheme, and you might perhaps wonder why I'm not using a flux conservative scheme for these things, because that would seem like the better choice for conserving mass. And the reason is I don't really know why, but the flux conservative schemes that we tested actually break the run after a while and introduce very difficult to understand errors in the nonlinear coupling of these equations. Another way of dealing with advection that a lot of people in geodynamics are using is particle-based advection, Marker in cell, as Taras was describing. And if you're using particle in cell for two-phase and reactions, there's two distinct problems. The first one is that if you have two-phase advection, you need to advect the solid and the liquid properties, so you need two sets of particles, making things more expensive. Additionally, the liquid velocity field is very strongly divergent, because the divergence of the liquid velocity scales with the divergence of the solid velocity by 1/π, which is the porosity. If the porosity is like less than 1%, that means that the divergence of the liquid velocity field is a factor of 100 to 1000 larger than the divergence of the solid velocity field, which means if you have particles, you're constantly doing population control, filling gaps and deleting bunched particles, and it's very difficult to actually figure this out. Additionally, the reactions actually couple so sensitively into the advection scheme that any little irregularity in the interpolation scheme between nodes and particles immediately shows up as numerical noise in the reaction rates, which can then build up because of the nonlinear coupling of all of these equations and completely disrupt the run. So essentially all we seem to know about how to do good advection schemes seems to not really work quite as well for the reactive problems, particularly in more complex geometries. They're quite well behaved in 1D column models, but we want to do more than 1D column models. And then the last one really is more of a challenge in terms of model formulation rather than the solver technology, which has to do with what would actually be a more appropriate parameterization for reaction rates that takes more into account, like for example, that there could be a temperature dependence of the reaction rates, and there could be a dependence of the reaction rates on the species-specific diffusion on the grain scale, also on the grain size, the reactive surface area, and so on. So we're really interested in trying to build more involved and more realistic parameterization for reactions that we can use in models. And this was like the first block, and so I'm just going to stop here for a minute and see if there's any questions around.
I've got a question about the advection scheme that you use. Did you try the Smolakevich approach, the MP data?
Way too diffusive.
Even with the correction?
Yeah, it's way too diffusive.
To answer the question, we haven't, but yeah.
Yeah, no,
it's more difficult than the second order upwind scheme that they are using.
Yeah, once in a distorting flow, they're surprisingly diffusive. We worked on this a long time ago. You haven't played with any. I've moved away from them, but some Lagrangian methods for these reactive flows have certain.
No, we haven't played with that. No.
Have certain nice properties that sort of combine some of the particle schemes on a regular mesh that you're using.
Yeah,
quite good.
It could be. Yes.
And why did you move away from them? Oh no, in finite elements, yes, we can do them, but and parallelism is always an issue. But Rich did some early work on parallel, and again on a uniform mesh, it's not such a big deal.
But isn't the divergence problem just as bad when you have semi-Lagrangian as fully Lagrangian particles? If you have interpolation errors in the fully Lagrangian case, I think you would expect to see a similar problem. So if you can solve it for one, you could solve it for the other.
No, you're just vectoring along the characteristics. Once you have the velocity field, as long as your velocity field trajectories are well, that's all you need to know. You're integrating along a trajectory of something else, the melting rate, or the source term. The divergence is not an issue. Because it's not flux conservative form. It's material derivative.
Yeah.
So.
So, but I see that there can be some, we can pick this up in discussions later this week, but it certainly is a challenging problem. So moving forward, I have now discussed about some of the processes that can happen relatively close to the melt source, and actually I hope that I have convinced you that thinking of the melt source as a discrete event followed by the discrete event of transport is really a misunderstanding of the system. This is an integrated system where much of the melt production is happening simultaneously to transport and couples to each other. And similarly, if we then follow the transport on into the base of the lithosphere where the rock gets increasingly cold and therefore the material properties get increasingly brittle, we need to deal with the fact that at some point there is a flow to fracture transition occurring in the rock. To again motivate this a bit further, I'm going to look at a problem of particularly magma extraction into the lithosphere and crust, where melt transport regimes flow across this transition from ductile flow in the mantle to brittle fracturing in the shallower crust. And we're really interested in finding an understanding for the dynamic evolution of melt pathways that lead to either emplacement or finally eruption of melts at the end of a journey. And to give you an idea of the wealth of ideas that is around to do with melt transport or melt emplacement in the crust, there's all sorts of different pictures, but what always strikes me when I look at these pictures is that none of them strike me as particularly physically intuitive. So all of them are sketches, which is because we really don't know very well how this works, and I've tried to, this is a figure from my PhD thesis where I've worked on these problems with Boris and Dave, where I was trying to kind of summarize all of the ideas around for how melt interacts with the lithosphere and crust, where it is being formed by either decompression melting or some volatile flux melting. It then moves into the base of the lithosphere either by compaction waves, by diapirs, or by some form of fingering instability, and once it is in the brittle crust, it can do all sorts of things like stoping or forming nested diapirs, ballooning diapirs, amalgamating dikes or sills, or flowing into extensional sections of faults. But I think this is one of my favorite quotes about this issue, where Alan Rubin said that it seems that the interpretation of existing field observations is hampered by an inadequate understanding of rock that can undergo both fracture and flow. That was written back in '93, and I think it's still true. We really do not have enough physical understanding of what exactly happens at this transition. So just bringing it back to the origins of magma dynamics, when we were thinking, or I wasn't there, when other people were thinking about viscous compaction. This is just a standard picture of how we understand viscous compaction. One of the most obvious features is viscous compaction waves. So typically the viscosity is constant for these calculations, and we can see these solitary waves which interact with each other. In 2D, these solitary waves take on, actually also in 3D, as circular geometry. And so this is actually a system that we can analyze relatively well and understand relatively well. However, this is not actually what can possibly happen in this shape or form in the mantle, because first of all, it's not constant viscosity, and secondly, if you actually do the scaling analysis of compaction waves against the viscosity gradient into the lithosphere, you notice that compaction waves become completely unviable after a viscosity of maybe 10 to 21 or higher, which is what you would expect to happen at the base of the lithosphere. So then question is, well, what additional complexity do we need to describe our models? And there's a couple of additional complexities that have been researched, and all of them lead to flow localization and additional complexity in the flow pattern. So the earliest idea by Stevenson was that if the viscosity is a function of porosity, so that it's weaker where there is already melt, then there's a positive feedback that the weaker spots attract even more melt and get even weaker, which leads to a form of channeling instability. Then if melt is dependent on weakened by the presence of melt, but also is shear dependent, so it's a dislocation creep viscosity, then we're all aware that depending on the exponent for the stress dependence, one can get close to reproducing these results by Holtzman and Kohlstedt's group of these shear bands in simple shear. And an interesting piece of information as well produced by Connolly and Podlachikov is that if we assume that the bulk viscosity, the compaction viscosity, is actually much weaker on the decompaction, where melt is driving grains apart, rather than on the compaction, where grains are being squished together to squeeze out melt. And if that is actually introduced as a function into the compaction viscosity, the result of it is these decompaction tubes or fingers that are like elongated compaction waves that can protrude into rock where otherwise compaction waves would not be stable. But taking this one step further, we also know from overwhelming field evidence that in the crust, one of the most prevalent features of melt transport are dikes or sills, which are tensile fractures which are filled by melt that travels through the fracture plane. And you can see a picture here, and there is some understanding of how this physics works in terms of a kind of a zoomed-in view looking at the crack tip propagation, fracture mechanics. However, we're really interested in how we can use that knowledge for our more large-scale geodynamic models. And so what we're trying to do, or what we did try to do back in 2013 and the years before that, is to come up with a magma mantle dynamics-like formulation that is extended to include viscoelastoplastic host rock rheologies, because that's what we find from lab experiments to be the best description for rock deformation. So rock deformation is made up of three different processes, one being viscous creep, the second one being elastic strain, and the third one being material failure if a certain yield stress is reached. And these can be formulated both for the shear part of rheology, but also for the compaction part of rheology. And it's controlled by the shear viscosities, by the shear and compaction viscosities, the shear modulus, and the pore compaction modulus, and then additionally by a plastic failure criterion which has to limit both the maximum shear stress amplitude that is allowed before material fails, but also the minimum compaction pressure. And I should remind you that compaction pressure is the negative of melt overpressure. So essentially this is saying that there's a cap on how much melt overpressure can be sustained in the pore space before a rupture occurs. And those fracture criteria, if we're just kind of using the simplest standard that people seem to agree on for the behavior of rocks, it would be a combined Moore-Coulomb-Griffiths-Morel criterion, which is here plotted in some simplified way, where there's a cohesive frictional yield surface for positive effective pressures or positive confining stresses, and it drops off quite steeply for tensile conditions where it meets the axis here at the negative magnitude of the tensile strengths of rock, which is not actually very large. It's of the order of a couple of 10 megapascals. And so the way that we implemented this into the magma dynamics equations is by having a constitutive law for shear stress and for compaction stress of these forms. We call this an effective viscosity approach because it is essentially writing the constitutive, the rheological law in a very similar form to a viscous law, just with some additional terms. So there is a term that looks very similar to the general viscous flow law, and then an additional term which takes care of the elastic stress evolution. So this is an elastic stress update, and here is the same equivalent for compaction stress or compaction pressure. And these effective viscosities and these stress and pressure build-up parameters can be found as a function of the normal viscous viscosity, the shear modulus, and additionally those failure criteria. In terms of implementation of this code, we implemented this one in finite element discretization. Unfortunately, we did it on stabilized Q1 elements. However, I'm still not quite sure what really the best choice would be to do it better than that, but I'm going to show you some of the reasons why that's actually a bad choice. We did the nonlinear problem with Picard iterations where we solved the velocity pressure problem, which is the same as I showed you before, and we separately solved here only the porosity evolution equation. So this doesn't have any of the thermochemical coupling, it only has that porosity evolution equation that Sander showed us earlier on. And in this case, we actually used the particle in cell invection scheme, and this is the reason why I noticed all of the different problems associated with it when trying to use this in two-phase context. And this was actually a MATLAB code which was only really viable for relatively medium resolution 2D runs, but that was what we did anyway. So in terms of simulation results, this is one model where this is a 4 by 6 kilometer box. There's an introduced batch of melt down there. Remember, it isn't reacting, so this is just could be any liquid, but we're calling it melt. We're putting an extensional strain rate on the box, and we're controlling the viscosity inside the box by giving it a constant background viscosity. So it's a constant background viscosity that is then modified by the elastic and plastic properties of the rock. And what you can see here in the strain rate field, so this is the magnitude of strain rate, is that due to the extensional strain rate imposed, stresses are large enough to fracture, so we have an extensional fracture regime coming up here, and if we run it a bit further in time, so after a couple of 10,000 years, we can find that there is this vertical, very localized pattern of melt, where you can see that it's no longer taking on the angles of normal faults, but instead is vertical with respect to the extensional stress direction. And this is the closest we think a continuum model can get to an actual dike. So across this, there's an extensional discontinuity in velocity components, and there's a positive accumulation of melt and melt flowing upwards inside this continuum scale fracture. And so essentially, this proves that we can use these rheologies to have a system where you go from flow to fracture in a self-consistent system simply by changing the properties of the rock. An interesting fact is that between the flow to fracture transition, so if we would impose a very low viscosity here, we would get either compaction waves or diaprism as the modes of melt transport. If we put a very high viscosity in, we get fracturing. And if we put an intermediate viscosity in and put it on the simple shear, we get this sort of pattern. And unfortunately, apart from Taras, who showed something similar before, and this simulation here, which is at the end of my thesis, this has not actually been investigated much further, but it seems that there's an interesting interaction at the transition between flowing and fracturing that can actually lead to melt shear bands that have some of the properties that we're looking for, motivated from experiments. And if we put this in sort of a regime diagram of the same setup as I showed you before for the fractures, and this is an axis of increasing rock viscosity and an axis of increasing tensile strengths, we can see that for high tensile strengths and low viscosity, in this case we form large diapairs. This is an unfortunate effect of the boundary conditions we've chosen, which supply a lot of melt and therefore create a large diapair. Otherwise you could imagine instead it being a simple viscous compaction wave. And in the other end member of hard rock and low tensile strengths, we find these fractures, and in between we find a wealth of different modes of deformation which all have to do with some melt-enriched shear bands which can take various geometries and various effects, but we just call them melt channels. And then obviously what we're finally interested in is to see if we then can plug this storyline together and put some of this non-reactive melt into the mantle down here. And so this is a strength profile with a strong upper crust, a strong lower crust, and a strong lithosphere. So this is a very strong lithospheric strength profile, and actually the depth of neutral buoyancy is imposed here at the upper to lower crust boundary. And then we run this, and you can see that there is so this is again on the extensional strain rate, so we find normal faults again, and then we can see that some diking actually uses an existing fault plane of a normal fault and that rotates the stress field such that it becomes a dike which transports melt upwards. We can see some pooling of melt in those low viscosity channels, particularly in the one that is also the neutral buoyancy. But again, melt really ignores the neutral buoyancy depths and goes all the way to the surface because it is driven by the excess buoyancy in the root of the magmatic system. And then in the end, we can even see like a little feeder dike going up into the surface. But I mean, all of this is very hypothetical. There's a lot of simplifications in these models, but it proves that we can actually write formulations and rheologies which allow us to look at the magmatic systems with the lithosphere and crust as one integrated physical system, and it I would also suggest that it is actually necessary for us to understand more about crustal magmatism, to understand it in terms of such an integrated system. If we only ever care about a single magma chamber or some imposed kind of cylindrical conduits that we just plug into reality because we think it should belong there, I think we miss a lot of the complexities that can arise, where there are, for example, branches that die out. There are mushy kind of zones which are not clean fractures in any sense of the word. And so I think there's a good motivation to pursue these models further. But again, there's challenges. These models are actually relatively hard to do for a number of reasons. First of all, there's the reason, one of the reasons why these are hard to do is to find a stable discretization that fulfills all of the criteria we want. And one of the key criteria we want and need of this is a discretization which is stable for both the zero porosity limit and the partially molten state. So we can formulate the equation such that when porosity goes to zero, the system of equation goes back to normal Stokes flow as we're used to it. But it is often found that, for example, in finite elements, those elements which have good local mass conservation properties for the Stokes system are not really suitable to do the two-phase system, and those that are suitable for the two-phase system have bad local mass conservation qualities if porosity goes to zero. So I believe that some people have already been discussing this during this workshop, and so this is plugging into an ongoing discussion. But as far as I know, there are still some questions associated with it, particularly for finite elements. What I can add to the discussion is that for finite difference staggered grid, this is a non-issue. This limit is absolutely stable and well behaved. So we have very nice mass conservation in the zero porosity limit, and we have a very smooth transition between the two regimes without having to fudge in the code. So there's really nothing that is problematic in this for the finite difference staggered grid, but finite element is a bit of a different story. But I think the most crucial problem with this system of equations is the non-linearity in the plastic flow law. And there was a recent paper by Mark and Dave and Kian that discussed this for the Stokes flow case of a simple shear band test of why the convergence of nonlinear rheologies with a failure criteria can actually be very problematic and maybe not solvable in some circumstances. And I would submit that if you then add magma dynamics and a second part to the failure criterion and more nonlinearity, it certainly doesn't make matters easier. And so actually producing rigorously converged solutions for these problems is quite tricky, and as many others in the community, these simulations have been produced by cutting off the iterations after a certain count that exceeded my patience. And so they are variably converged. They converge actually with the help of elasticity. They converge reasonably well in most cases, but there's always a number of time steps in any given simulation where they do not converge, and we just simply decide to move on. This is not satisfactory, but it is also not solved at the moment. So this is where we stand. And then the last one is that there's an inherent resolution dependence of these flow localizations, because these fracture-like flow localizations would physically like to localize below what is allowed on our grid resolution. And so if we then run a control simulation with half the grid resolution compared to what we do here, we'd find that the fractures look slightly different. They would have the same orientation, they would start at the same point, but instead of having one big one in the middle, you could easily find two parallel ones next to each other. And so the pattern can change, but the overall predictive power of this, of predicting the directionality of fractures and where they would set in a certain context, I think is still powerful enough, even though we have some problems associated with it. And so, yeah, those are the challenges of approaching the flow to fracture transition. But on the other hand, there's a lot of wealth coming out of those models that I have not had the time or not even attempted to discuss here. And also, it would be really nice to see other codes in the community reproducing some of these results or bringing them a step further, because so far there's barely any codes in the world that have addressed these problems. And so it would really be nice to get some more people on board for these. So if you are interested in looking in that direction, please do find me after the talk and let's talk together. And that was all I had to say, and I'm just going to leave you again with this kind of integrated view that is wrong but pretty. Thank you.
questions for Toby? Please, Sean.
There is a very strange but interesting volcanism that was discovered a few years ago in oceanic area along the ocean trench. This is called the putty spots.
Yeah.
And I really like to see how you guys, theoretians, explain this, because this is very strange.
Yeah,
Anomalies, when they try to find them, almost ubiquitous, along the trench, in the ocean side, very tiny magmas there.
I've actually discussed with a couple of people who are working on petty spot volcanism, and one idea that we've discussed but we've never come to a conclusion, so this was the product of some discussion with no proper end to it, is that if there are these low fraction melts that get stuck along the flanks of the mid-ocean ridge, because at this stage, at this distance from the ridge, the cooling rate at these steps is actually quite low, it is possible to think that some of these pools of enriched volatile content can stay either partially molten or very close to their solidus for most of the age of an oceanic plate, and once the forebulge is bulging up in front of a subduction zone, you could potentially remobilize these melts and also produce a fracture environment where some of them can be extracted, but they would never be large volumes, and they would potentially have a very interesting geochemical makeup because they've been fractionating from very deep, incompatible enriched melts. So that would be the direction in which I would start looking. But I don't know if that's the solution to the conundrum.
I had a look at their composition some time ago. They're the same as ocean islands, right? And they're not, despite the claims that some of those things are very, very far from any ocean bulge. I don't think there's anything special at all about the petty melts. They're just small melts like the ocean islands. They've got the same isotopic composition, they've got the same elemental composition. They're just not very big. And I think it's part of the general problem of understanding how you get ocean islands. And I think I agree absolutely with what you say. I think that they're just simply like the ocean islands. They have this strong isotopic signal. They've been enriched for a very long time, and that's very typical of the ocean islands. I think it's part of the general problem, which is not part of really what I mean. It's not, I don't think they're related to ridges.
Garrett?
Yeah, it's good that you had this figure up because I had a question about it. I was just curious, what controlled the length scale of the fingers from the this volatile channeling?
Do you mean the spacing or the lengths along the vertex?
The width and spacing.
So the spacing is controlled by the compaction lengths. So it's
The upper limit.
yes.
Right.
So but also the width of them is essentially controlled by the ratio of flux going through the channel compared to the total flux going across the whole distance, which actually also means that if you would refine this to a smaller grid resolution, you could localize a larger flux inside these channels, which would make them more narrower. So the general pattern of where channels emerge and how far they protrude stays the same. We did a resolution test on these, but the actual pattern is variable and transient. So here again, flow localization always has this slight grid dependence associated with it.
Other questions? I have a question for you, Tony. In a lot of the later talk, you saw porosities that go to much above the disaggregation threshold, and in some cases, these are isolated blobs, which the dynamics of which is probably not very interesting. They just get stuck. But in other cases, you have the hope of approximating dikes and propagation along faults where viscous resistance to flow is, in fact, part of the governing balance of forces. And a priori, I think one would say that the formulation doesn't correctly model the balance of forces in those situations of high porosity in a narrowly confined place. And of course, you would never take if you wanted to model, say, a magma chamber or a fully molten body, you would never start with these equations anyway.
Yeah.
So how do you respond to those kinds of issues?
Well, first of all, in our approximation of what we call dikes, they invariably never have 100% melt in them. They go to 20 or 30% melt, and that has to do with the fact that the efficiency of localization is limited by the grid. And so they would actually like to localize further down and be pure melt. But because of our limited resolution, they stop, and so they never accumulate pure melt. If they did accumulate pure melt, then the only thing from a geodynamicist's point of view you could approach the problem with is as a variable viscosity Stokes problem, where you make sure that the viscosity inside the dike, where it's purely molten, has a large enough viscosity contrast to the surrounding rock, so that it is essentially stress-free with respect to the surroundings. It doesn't support shear stress on any magnitude comparable to the wall rock. And there are ways that you can effectively deal with the equations that limit is recovered, sort of, but not in a very satisfactory way. So I think it is an open issue that we should discuss how to deal with these things, but essentially you'd want to cast the equations in a way that as you approach the phi equals 1 limit, your system goes into a variable viscosity Stokes system where the viscosity of the pure magma is captured on a level that is resolved on the grid on which a geodynamicist is dealing with, but is not disrupting any of the surrounding dynamics by supporting more shear stress than it actually should. So that is roughly the idea of where I'm looking into, but it would also have to make sure that there is no further divergence of velocity allowed in that limit, because it really has to go to incompressible Stokes again. And so there might be some effective cutoffs or some additional terms in the rheology that could take care of this. But for me, it's not a settled question.
Okay. Oh, Dan, please.
One of the things which has come really from the recent eruptions in Iceland, and also from looking at past ones, is that the diking is essentially a three-dimensional process, and the melt accumulates quite slowly over a long time in some magma chamber, and then fractionates, and it's the fractionated melt that you see doing the diking. And I wondered how that connected up with how important is the three-dimensional part?
Well, I mean, I'm absolutely aware that the three-dimensional part is something we're not dealing with, and all of these obviously assume that there's an infinite geometry going into the plane of view here, and that would change the energy balance on all of the mechanical processes we see, because they don't only have two sides of confinement, but they have a three-dimensional confinement. So I think it's going to matter hugely. But to address the second part of how you formulated your question, where you have a fractionation and a pooling going on before fracture is initiated, this is essentially what you see here. This yellowing of the colors here is because you crystallize and fractionate, and then at some point some of the melt finds its way into a fracture. However, I would advise that we slightly step aside from the usual thinking of having a chamber and fractionation happening in that chamber, and then a fracture coming out of it, because fractionation is something that is constantly ongoing as soon as melt invades a space that is essentially cooler than what the melt would support. Fractionation is not something that is confined to a kind of a static geometry of a chamber, but fractionation is something that accompanies the whole melt transport regime. And so I think some of our thinking about how melts get to the final level of fracturing and eruption is probably limited by our typically static interpretation of what we see. And I would suggest that we should just extend that a little bit more into an integrated view of a whole journey of a melt across a crustal system, where fractionation can happen in all sorts of circumstances.
No, I was actually thinking not in terms of people's concepts, so much as actually what has been observed in the Afar and in northeast Iceland, and there the melt certainly does collect into something over quite some period of time, and then the diking episode is very closely connected with the release of the elastic energy from the plate motions.
Yeah,
right?
Yes.
And the melt there is fractionated. It's fractionated in the crust, not in the mantle.
Yeah.
Right.
Chloe?
Just to follow on Dan's comments, I also think that the stratification of the crust in composition is essential to understand the flow that goes from porous flow to fracture, because in fact med pools below stratification at a given limit. But I have another technical question for you.
Chloe, can you, in the next part of your question, speak louder because the people in the back can't hear
Okay,
you?
sorry.
Or just repeat the question later.
Can you repeat the question, please?
So just a technical question about one of your simulations where you show a fracture going from the bottom to the top. I was wondering, but maybe you said it, what is the boundary condition of the surface?
It's a free surface boundary condition. So the question was, what is the boundary condition on this simulation here? And it's a free surface. Let's see that again. I'm not sure if you actually see some of the topography because it's not very large, but here you can see a bit of shallowing between those normal faults. And actually I think it's an important point to mention because the free stress boundary condition on top is absolutely necessary if you want to look at long-term tectonics in the lithosphere and how magma interacts with it, because just a simple flat, no-slip boundary condition or a free-slip boundary condition will actually modify the stress states in a way that would govern where your melt could travel to and where it couldn't. But that is also an additional thing that we need to be aware of when we're building code. Finite element provides you with an easy way of doing free surface. Finite difference, most people would resort to something like either an internal boundary condition with a discretized stress-free condition or then a sticky air approach. But it is an important ingredient in these models, that's true.
Was there something in the back? Yeah. Charles?
Yeah. Can you comment on this dikes propagation? Do you only observe this vertical structure in background extension models, or have you ever seen in unstressed model this vertical tendency of propagating the dike?
I have not yet seen any vertical propagation. You mean just under its own buoyancy, for example?
Yeah, like from whatever feedback, say you start from reaction channel, and then it suddenly start to go into the viscoelastoplastic part of the lithosphere as a dike.
No, I have not, and I think one of the reasons why it seems to be hard for dikes to emerge just under forcing different from extensional tectonics is, I think one of the possible reasons can be the 2D, which means that if you don't pull from the sides, you actually have quite confining conditions, whereas in 3D, the stress states can be more complicated and can allow for locally extensional stress fields, whereas everything else might be compressional. So that could be one reason, and the other reason is the resolution issue, because you essentially need to start a fracture, you need to have a stress concentration in some heterogeneity along some melt flow structure. And the finer your resolution is, the higher the stress concentration you can get. And so that could be one of the limiting factors why we do not see a lot of spontaneous fracturing, but only kind of when we properly pull. Mm-hmm. But yeah, that could be enhanced by using adaptive mesh refinement, for example, but it is challenging.
If I could just ask one more question, Toby. I recall from earlier hearing about this stuff that there is a kind of memory of the rock in terms of its previous damage or plastic failure. Can you just specify a little bit what you've done and how important it was, both numerically and physically?
Yeah, so in this simulation here, we've introduced the strain weakening, where at each time step we calculate the plastic component of strain being done and then integrate that and place it on particles and vect it along with the flow, which means that these, let me see if I can, no, I can't quite easily. No, it doesn't let me control, but as you saw, there was like these fractures that form here. And this fracture essentially is accumulating plastic strain, which is then leading to a linear reduction in friction angle. And so by the time that the melt arrives here, it finds this to be a weak spot in the lithosphere and therefore follows it. But in all the other simulations, like here, we have applied absolutely no strain weakening. So this is just an instantaneous failure of where the stress conditions allow it. And so it is an important ingredient, I think, if we want to look at long-term tectonics, because material does have a memory. If it has fractured at some point, it has lost its cohesion, it will heal over time again. If there are major faults that have been active over a longer time, they are going to be the preferred locus of further deformation. And so I think our models should contain some form of damage and plastic strain memory. However, how to do it is a completely different question. I think people have quite different views on how it should be done. I've so far, when I've used it, always gone with the pragmatic solution of just having a simple linear weakening of friction angle between some onset minimum strain and some maximum strain that you accumulate. So that's just the pragmatic, simple solution.
Thank you. If there's nothing more, then we will break for lunch and reconvene at 2 in about an hour and a half. Thanks, Tony.